mobile IUI, session number 1. There will be a second session coming tomorrow on the same topic. We have 6 papers as part of the session. We have 3 long papers, followed by 2 short papers, and 1 from TIIS. I'll introduce myself. I'm David Gotts from University of North Carolina at Chapel Hill. And our first speaker today is Yan Wang from Columbia, and he'll be talking about a paper called Panoswarm, Collaborative and Synchronized Multi-Device Panoramic Photography.
Thanks for the introduction. Good afternoon, everyone. I'm Yan from Columbia University, and it's my great pleasure to share our work, Panoswarm, with you guys and learn from you. Panoswarm is a system about collaborative and synchronized panorama photography, and it's a joint work of Columbia University and Adobe Research. Panorama is a very popular way of taking photos. It can provide a stunning, super wide-angle view of the scene. And here is an example of panorama taken by me of the skyline of the New York City downtown. And here's another example that I took 2 days ago in the Stanford campus. It actually contains 330 different photos, and I warp it to a small planet effect. It's a special viewer effect. And then we can see that because of the flexible forms and also the stunning views of the panorama, it's becoming more and more popular and has been integrated into different mobile operating systems such as iOS and Android. However, if we take a closer look at the result image, we can find some artifacts. For example, here, for some tourists, like the tourist in the right, his body and legs are misaligned. And there is another person that only has legs but without a body. And this is a well-known drawback of panorama named the ghosting effects in the photographer community. And people know well about it, and if you search online, you can find a lot of funny or sometimes embarrassing pictures of panoramas like this. And people even intentionally make fun of it with this drawback. And this actually inspired our work, Panoswarm. Not everyone likes photos of this, because if you want to keep your memory with a panorama, you don't want to see some ghosting effect. But before we dive into how we solve this problem, let's first have some understanding of how a panorama is stitched and why this happens. A panorama is stitched from several individual frames. And for each pair of frames, if they have sufficient overlap, the computer vision algorithms are able to adjust their scale, rotation, and translation to enable their overlapped content to be aligned properly. For example, in the New York City panorama here, it actually contains 5 different frames. After proper alignment, the algorithm thinks, oh, we should put the first frame here, and then the second frame here, so that the content of their overlapping part will be properly aligned. And so are the 3rd, the 4th, and the 5th image. After blending and cropping properly, we are able to get the final result as shown in the right corner. This looks perfect when the scene is static, but things begin to go wrong when there is a moving target. For example, here, it is a panorama with three different frames, and the photographer was sweeping the camera from the left to the right, and there was a horse moving from the right to the left. Here's the first frame. We can see the blue rectangle shows where the horse is, and therefore, in the first frame, only part of the head of the horse appears in the frame. And then here's the second one. Because the horse moved, now only part of the body shows. And here is the 3rd frame. Only part of the tail shows up in the 3rd frame. It makes perfect sense for every individual frame, but if we put up them together, it makes a really funny panorama. And therefore, the reason of such ghosting effect is because the frames are not taken at exactly the same time. And how to solve this problem? We are not suggesting the users to swipe 180 degrees in 0.001 second. That's simply impractical. But if we think it from another way, if we have 3 different devices pointing to 3 different directions and let them take photos at the same time, then it looks like things will be better. And we're very excited about this idea because previously photography is an activity that only one single user is involved. But now it can be a collaborative task multiple people can take part in that, and we can make it a social event. We are especially curious about 3 questions. One is, what can we do with the idea? What applications, what apps can we build? And 2 is, in this process of building a practical app, what technical challenges may we encounter and how to solve them? And 3rd is, from a social perspective, can we inspire some new interaction experience from social side? And therefore, the remaining of this presentation will be divided into workflow, implementation, and evaluation. In designing the workflow, we specially follow the design guidelines of A, encourage social interaction, and B, make the UI easy to follow. We do this prototyping process in an iterative way, and after several iterations, we find 3 key points should be followed to make it easy to use. We should have easy to follow workflow. We should have everyone should have a clear role so that you will have a clear expectation of what to do, and the process should enable the user to adjust their panoramas fast and end fast. Otherwise, the system would be inefficient. And here's a demo video of how the system works. We have 3 different users. The users have either an iPhone or iPad as the device. At first, everyone has a QR code shown on their device, and then they scan the QR code to form a swarm or a group to take panoramas. Then the capture sessions begins. And on the screen of every user, it contains 2 parts. One is everyone can see the camera view of all the other users, and the other is there is a panorama preview here. There is a host user, that is me in the video, controlling and coordinating everything. At first, we can find everyone is pointing to the same direction, which is bad for a panorama. And therefore, I instruct one of the users to turn a little bit right by swiping on the screen on that specific user's preview. And this will get the app to render a red arrow of the same angle on that user's screen. And therefore, in the video, we can notice that the lady in red then turned a little bit right, which effectively increased the coverage of the panorama, which is shown in the real-time preview. And when everything is ready, I tap the photo button, and then all the devices take a photo at the same time, which is ready for panorama stitching. And therefore, more specifically, this workflow is divided into 3 stages. First, the users form a swarm by scanning their QR code. And the second is they adjust their position and angle to get ready for the panorama stitching. And the third is all of the devices take a photo at the same time. For the first part, when the app first launches, there will be a QR code shown on the screen. If a user A wishes to join user B's swarm, A simply scans the QR code of user B's, and then the 2 devices will send signals to our backend server, and then the server knows, oh, these 2 guys are from the same swarm, and I will send control commands to both of them. And for the second step, the users will see 2 parts in their interface. One is individual camera views, so that you will know what are the other users looking at. And B is a real-time panorama preview, so that you will have a big picture of what's going on, what the final panorama would look like. And the host user will instruct them by either verbally telling, oh, user A, please step forward a little bit, or more accurately, she can also swipe on the screen to let the app render a red arrow on that specific user screen. And technically, how the real-time preview is done is we have a backend server, and every device is sending their real-time thumbnails of the camera images to the server. Then we use existing algorithms to stitch a downsampled version of the final panorama. Nothing fancy here. We don't do any specific optimization like nonlinear warping or sub-pixel level alignment, etc. So this turns out to be pretty fast. With an i7 processor, we are able to get 20 frames per second and in a local Wi-Fi network. And when everything is ready and we are ready to take photos, how to synchronize all the shutters? The solution is simple. We found that even the host device sending out broadcasting on the network for a signal would work. At first, this looks, oh, would it be so simple? But after we getting some experiments, it turns out to be true. Here we have a screen showing millisecond level changing timestamps, and we have 2 devices taking photo of the screen at the same time with this mechanism of shutter synchronization. We then compare the photos to get the difference between a timestamp shown in the photo. We found that with a local Wi-Fi network, we can get time difference less than 40 milliseconds. And with 4G network, we are able to get time difference less than 100 milliseconds. Considering that the exposure time of taking a photo is actually in the level of tens of milliseconds or 100 milliseconds, it's quite acceptable, and we didn't observe artifacts in our result image either, as will be illustrated later. Then, back to our design guidelines, we accommodate the design guidelines by dividing our workflow into clear stages and introducing an owner to coordinate everything, and also introducing a real-time panorama preview to engage all the users. Then, after looking at the workflow and implementation, here is our evaluation. We recruited 2 groups of users who often take photos with their cell phones and have different levels of familiarity of taking panoramas. At first, we train them, like that is, I act as a host user and give them devices to take a panorama, actually use our app to take the panorama so that they will get familiar with our system. Immediately after the training, we ask them to take panoramas in 3 different sessions of highly dynamic scenes. And in this process, they also don't provide any help except resolving some technical issues. And after each session, we do a debriefing to see what they think about the system. We're especially curious about several questions. We are most interested in, does it work? Therefore, we provide a comparison of the iPhone's internal camera app's result and our result. Here is one example. The top row is from the iPhone, and the second row is from our app. We can see that in this dynamic scene with walking pedestrians, iPhone's panorama shows like 4-leg pedestrian, but our app got it right. And here is another example of New York Street view. We can see that there is a ill-looking truck on the street from iPhone's result, but our result get even high-speed moving objects like flying birds and moving cars right. We also asked the users how they think. They confirmed this comparison that they found iPhone's internal app lacked the ability of handling dynamic scenes, but our panel swarm actually does a good job because they didn't find any people being cut off in our result. We also measure the time spent on each session. We found 2 interesting observations. One is the average time per session dropped after the first trial, which means the users may need time to get familiar with the system. And the second observation is the size of the group really matters. That is, for a 4-user group, they take around 50 seconds, but for 3-user group, they take around 30 seconds to accomplish the task. We also asked about the users that whether they will share with like friends or strangers, and the answer is possibly some users think they will use it with friends, and some of the users think possibly not, although because it's time-consuming, but for some events with a lot of friends, possibly they will use it to keep memory. But for strangers, most of them think, oh, possibly not, because it's not really designed for strangers, but it's okay to use it as a conversation starter. We're also interested in the scalability. We tested to 8 devices and didn't find any issues with the network. But our CPU, backend CPU, does reach 100%. But this should be easy to resolve because the matching algorithm has a linear complexity on the device, the number of devices. And if we can use the mobile sensors like gyroscope readings, hopefully we can restrict the search space to make it even faster. We have some final observations that the host usually use verbal communication to instruct the team members to step forward or backward, but use the graphical interface to instruct them to turn, possibly because our GUI doesn't have the capability of telling them to step forward or backward. And some users are not satisfactory with the design of the host user, and they wish everybody should have fun. So basically, that's it. We have some takeaway messages that we wish you to remember even after the presentation. Basically, the idea is photography shouldn't be one person's event. It can be collaborative. And one simple example application is we can take panoramas with that. And to get a successful system, the key design guidelines should be everyone should have a clear role assignment. We should keep users in the loop, and we should encourage users to have social interactions during the process. The key techniques to build such a system is the QR code is useful to efficiently build a swarm, and the synchronous chatter can be done simply by broadcasting a signal around the network. About the future work, we are thinking about, instead of pointing the camera outward, we can actually bring it inward so that there may be some very cool demos from that. This is done from our initial experiments. That is, we can build some bullet time effect from that. And you're also more than welcome to scan the QR code to get the latest progress. Thanks for your attention.
For questions, if you want to come to the microphone.
Hi, this is Cheng from Georgia Tech. So very interesting work. So seems like your idea is to solve that like ghost effect by taking more pictures.
Right.
Take more pictures and combine them together.
And at the same time.
At the same time, right?
Yeah.
So it seems like take one picture by 3 people will cost like 1 minute, something like that. So it's still longer than what we usually do. So have you think about other future work? Like if you have multiple cameras confirmed on one device, it will do the same job. Like you have 3, like for the phone, you have 3 cameras pointing to different angle. So you will still get like a wide angle and combine like the picture later together, but without like users' effort.
Right, this is actually a very good point. And we have different user scenarios and had this idea before. The idea you mentioned is we can have a specialized hardware.
Yeah.
So that they can, with one click, they can get the panorama right. And this is definitely worthwhile to do, but this is for like professionals. And I agree with you, this is effective, but our paper is for the consumers. That is, everyone can form a group with flexibility and no time, and it can also be a social event. So that's the fun side, and you are the professional side.
Cool, thank you.
Thank you.
So while we switch to the next speaker, I have a quick question. You talk about the scalability performance for up to 8 with CPU time and those kinds of things. You mentioned times for 3 versus 4 users. Have you tried looking at how long it takes the actual users to just organize themselves when you get up towards 8 devices, or you haven't looked at that?
Unfortunately, we didn't do this. We only, for the scalability, we only have several devices and the algorithms running to load, to stress test that algorithm.
Got it. Thank you very much.
Thank you.
Let's thank our speaker one last time. All right, our next talk will be delivered by Melissa Romilly from the University of Southern California. She'll be talking about her work on recognizing human actions in the motion trajectories of shapes.
All right. And this is work I did with Soja Marie Morgans, my advisor Andrew Gordon, and Louis-Philippe Morency. So in 1944, there were 2 social psychologists named Fritz Heider and Marion Simmel that made this following short film, which I'll start playing. The film simply shows some moving shapes, as you can see. Specifically, we have a circle, 2 triangles, and a box with a hinged opening. And they did this as part of an experiment where they showed this film to people and asked them to describe what they saw. And they found that people largely described the moving shapes in terms of human behavior. And so they told, the shapes were human characters, and they told stories about the relationships between these characters and their emotional states and their intentions. So the finding for this study was that people naturally perceive the world in terms of human behavior, even when what they're perceiving is not human. So here is an example of one participant's account of the film, and I won't read it all, but what I want to point out is that there are distinct actions being described in the story, and these actions seem to encode the shape's movement throughout the animation. So this participant perceived the highlighted actions like shaking, fighting, following, racing, and chasing based on motion patterns. This participant attributed psychological states to the characters based on these perceived actions. So the recognition of actions in this film seems to be a really important foundation for constructing a story about the film like this one. So if people can do this task of recognizing a human action from the motion trajectory of a shape, we wondered if this task could be modeled by a computer. So there's a lot of existing work on using machine learning to recognize human actions in videos of people. So we decided to explore some of those similar techniques for this more abstract action recognition task. So the data that's needed to encode the hider and symbol animation actually lends itself to a machine learning approach because it's a straightforward encoding. The animation is just composed of a sequence of position and rotation values, so for each shape across each time point in the animation. So the goal of this work is to classify the actions depicted in an animation like this one according to how people perceive them. So in order to apply a machine learning approach, we need data, of course. So we had previously designed a data collection platform called Triangle Charades, and this was actually presented here at IUI 2 years ago when it was in Haifa. So without going into too much detail about that paper, the summary is that a Triangle Charades is a game where people are given action labels and then asked to create animations of triangles depicting those actions. So the animations players create are then shown to other players, and these other players must guess the action the author was trying to animate. They're given a set of 6 action labels to choose from when they guess, and if their guess is incorrect, meaning it's not the intended action of the author, then the player continues making guesses until they're correct. So just quickly, I'll show you an example of the author's intended action was in circle, and so they made that animation, and then this is the guessing interface where the guesser has to select in circle. So, and that's what they did. If you can look at the paper for more details about how we came up with the action labels for these animations. Ultimately, we distinguish between actions performed by a single character and then actions involving 2 characters. And the final label set then includes 31 one-character actions and 31 two-character actions. And this is far more labels than any previous work related to abstract motion perception has considered. So using the Triangle Charades game, we created a data set of animations where each animation corresponds to one single action label. And we recruited players via the crowdsourcing platform Crowdflower, and a few additional players came through self-sign-up. So in the final data set that was created by these players, we filtered out animations that took the guessers, on average, more than 3.5 guesses to correctly identify. So this would be, 3.5 would be random chance. So the final data set included 2,060 animations of one-character actions and 1,158 animations of two-character actions. So we evaluated 2 different machine learning approaches for the task of recognizing actions in these charades animations. The first one we refer to as a spatial temporal words model, and the second one is a recurrent neural networks model. So here is a diagram giving a summary of the spatial temporal words model. This approach is actually analogous to the bag of words approach that's very popular in text classification. Of course, here we're not classifying words, but we define a spatial temporal word as a categorical representation of the motion at a particular duration, the animation. So this approach has actually been utilized for video-based action recognition, so there's some motive to explore it for this task. So to apply this approach, we split each animation into uniform length intervals, and we computed the motion features of the shape's trajectories at each interval. So see the paper for a specific description of the features that we used, but these were things like distance, velocity, curvature. Using the feature representation of the intervals, we applied a clustering algorithm to them. And so each resulting cluster center was then treated as a word in the vocabulary. So subsequently, we transformed each interval into a word by assigning that interval to the closest cluster center, so the closest word. So each animation was encoded as a bag of words vector, and then this was given to a classifier to predict an action label based on the words in that animation. And we tried 2 different classifiers, a logistic regression classifier and a Knight Bayes. Okay, so the second machine learning technique we tried was a recurrent neural network-based model. Recurrent neural networks, RNNs, have become very popular for modeling sequence data. And I won't go into the details of how recurrent neural networks work, but basically the scheme for our task is that there's an input layer that encodes the shape's motion trajectories in the animation, and a hidden layer that learns a feature encoding of this data. And this feature encoding is then used by the output layer to classify the action in the animation. So in this diagram, there is one single hidden layer, but people among the deep learning community have found that if you start stacking up these hidden layers, you get better performance for many different tasks. So for our work, we tried both a model with a single hidden layer and then a two-layer model. So to summarize the main distinctions between this model and the spatial temporal words model, for the RNN, we don't split the animation into intervals like we did to compute words with the previous model. So the trajectory data at each frame of the animation is directly encoded into the hidden layer. And secondly, we don't tell the RNN what motion features to use for classification, like we did this with the words model. The network just automatically learns what these features are as it observes animations during training. Okay, so some results. We applied these two approaches to recognizing actions in the charades dataset. We trained separate models for the one-character and two-character datasets since they had separate action labels. This table shows the results in terms of accuracy, and as a reference, the majority baseline is about 5% for both types of animations. And so we found that the one-character accuracy was lower than the two-character accuracy across all models. Among the one-character animations, the spatial temporal words model that used logistic regression for classification was the only model to significantly outperform the baseline, and this attained an accuracy of 12.6%. Among the two-character animations, all models showed improvement over the baseline, significantly over the baseline. The model that obtained the best performance was a two-layer RNN with a 25% accuracy. So the discrepancy between the one and two character results suggests that the relative motion between the characters was particularly informative for making these classifications. And in general, the accuracy of all models seems pretty low, but I'm going to present a different way to view the results by comparing them to players' guessing statistics from triangle charades. So here's that comparison. So remember that triangle charades players recognize actions and animations by guessing from a set of 6 labels. So we actually simulated this guessing scheme with the models. So for every guessing round completed by a human player, the classifiers also guessed a label for the animation from the same set of 6 choices shown to the player. And each model would guess by selecting the action among those choices that it assigned the highest probability. And if this was wrong, it would predict the action with the next highest probability. And then this continued, of course, until the correct selection was found. So this diagram shows the comparison between human and computer performance, specifically for each action. It breaks it down by action. And we see the average number of guesses it took to select that action by both the humans and the model. So remember that more guesses means lower recognition performance. And specifically what we're looking at in this graph is the spatial temporal words model with logistic regression, which was the best one-character model. And so you can see that the humans did better than the model at identifying one-character actions. So overall, the average number of guesses for the model was 2.6 guesses, and this is compared to 2.1 among the players. So the players outperformed the model among the one-character animations. So the two-character results actually provide a different picture. So here's the comparison between the human players and the best two-character model, which was the two-layer RNN. The average number of guesses across all actions was actually the same for the RNN and the human players. It was 2.1. And so interestingly, the distribution of this graph reveals that there are a few actions that the model almost always gets right on the first guess. So these are actions, if you can read these labels, these are lead, avoid, push, examine, and chase. On the other side of the distribution, there's of course actions that the model struggled to guess correctly. So there is this kind of spread across the accuracy of the model, whereas the humans were more consistent across different actions. for the recognition performance. So we created a second data set of animations that we call theatrical animations. And these animations are meant to resemble the Hyder and Simmel film. So in addition to a big triangle and a little triangle, these animations feature a circle and a box with a hinged opening that people often perceive as a door. So in contrast to the charades animations, these animations include more than one action label per animation, just as the original Hyder-Simmel film contained several actions. And the data set has 100 animations. The actions in each animation are labeled, as well as the characters that participate in that action. And these animations were created using an interface that was very similar to the triangle charades interface. Here, the players were given all 4 shapes, and they could animate shapes freely however they wanted. The result was just constrained to be a 2-minute film. So a trained annotator created 100 movies, all portraying different action sequences, and then labeled the action sequences using the same label set from the charades data set. So here's a very short example of a film where the annotated sequence is the circle argues with the little triangle, the big triangle pushes the little triangle, and the big triangle pushes the circle. Ultimately, we want to be able to recognize sequences of actions in these animations. So we made a baseline attempt at this by applying the models trained on the charades data set to predict the most probable action at each segment in these animations. This baseline performed pretty poorly, so there is a wide opportunity for innovation here on this task. So concluding, what we got from these results is that machine learning can be used to model human perception of motion, but motion does not seem to be able to fully disambiguate one action from another, or at least our models could not demonstrate that. So what we need to consider is that we might need to establish a narrative for an animation in parallel with interpreting the shape's movement. So as future work, we're considering how to integrate top-down knowledge about the narrative context of an animation into the action recognition task. And our data sets, both the charades data set and the theatrical data set, are actually available on this GitHub page. And thank you.
If anybody wants to step to the microphone. While we wait, I will, we can switch, I guess. I have a question about the chart you showed. So the prediction accuracy, or the accuracy of the labeling for your automated ones, you mentioned how some of them were really easy, some of them were really hard. Did you do an additional analysis to see what aspects made things easy versus hard? All right. Any other questions? All right. Les, thanks. Melissa, one last time. All right. Our next talk will be delivered by Prajwal Podyal from Arizona State University, and he'll talk about his group's work on Scepter, a pervasive, non-invasive, and programmable gesture recognition technology.
Thank you for the introduction. I am Prajwal, and I did this work with Dr. Ayan Banerjee and Dr. Sandeep Gupta. So this work is basically, we are trying to see if there's a way to use wearables for gesture recognition and trying to make it more usable. So I love this quote. It says, "The single biggest problem in communication is the illusion that it has taken place." This is true in day-to-day communication where two people communicate and they speak the same language. The person that is trying to say something assumes that he said what is meant, and the other person assumes that he understood what was said, but there's a gap. And this is especially true if the two people don't speak the same language. And for our case that we are investigating, it is the case in which one person cannot speak at all, so they use sign language. and the other person usually will not know sign language because only a small subset of population actually can understand sign language. So we are trying to see if we can facilitate the conversation between users of sign language and people that don't understand it. So we did some usability studies and asked users what would be the most important thing that they would want in such a system before we started work on it. And they suggested that it had to be real time to support an actual conversation, and that it had to be non-invasive because there's already a lot of stigma associated with using like heavy equipment, especially in the deaf community, because they don't want to be singled out. And the other thing that was also proposed was that it should be programmable, because some specific fields, let's say for healthcare, not all English words or technical words that are used there have equivalent in sign language literature. So it is very important to give the user the flexibility to train their own words. And this is also true if they were to use some different sign language which varies by locality or country, etc. So all this would hopefully lead to high adoption rates, and that was a driving force. So for this talk, we will talk about why we need sign language systems, which we've already touched upon a little bit. And we will see how we take sign language and the specific things about sign language and make or like model this system. And then we'll talk about some related work, what's already existing out there, and some future work. So, so the basics of sign language is that it is composed of hand shape, which is the shape of the hand that it assumes. So if you look at the pictures, the two signs are for the number 2 and number 3. So it's only varies in the number of fingers that are up. And the orientation is different. Can be different. So is the hand facing outwards, inwards, sideways, and how does whether if it changes while the sign is being performed, so the orientation can change. And also the meaning is also different if the location of the sign being performed. Say, for instance, a pain sign right above the head would mean a headache, while around the stomach it would mean stomachache. And also the movement from one location to the other. So now we'll talk about some of the challenges that we that are there inherently in sign language recognition. So the two hands combine to perform a sign, and they can combine synchronously or asynchronously, and they may be adding to each other's meaning, or they may be completely different and conveying some other information. And also there's a segmentation problem, which means that it is difficult to figure out when a sign ends and the other one starts. And also, like we talked about, the two hands can have relationships with each other to convey the meaning. So one of them might be the dominant hand, and the other one is just a reference. What we deal with in this work is mostly hand gestures, although sign language does have gaze, torso movements, facial expressions, etc. And one of the other challenges is that two signs may be very identical, and they will differ only very slightly in one of the modalities. I'll talk about modalities here in a second. For example, these two signs that you can see, the first one is the sign for eat, which is basically this movement twice. But the other one is the sign for pizza, which is also the same movement, but your hand is twisted. So the recognition system should be able to figure out things like this. So the overall problem is that so the database would have features and label, and it would have a bunch of those. And when a person performs the sign, we would collect some signals from them, convert them to features, and try to match the features with those in the database. And we will get the shortest distance, and then sort the results to basically output the one with the highest rank or the lowest rank. So we focused on understanding sign language because understanding the modalities helped us choose appropriate sensors. So this is a chart that demonstrates how important data is, but since we focused on making this platform usable and extensible, we only asked the user to train the system 3 times, 3 to 5 times for each new sign. So we don't have a lot of data. So as you can see here, if there's a lot of data, even if we don't know a whole lot about the underlying process, you can get good results. But if you don't have a lot of data, then it is fundamental to have some domain-specific knowledge or knowledge about the underlying process. So we went through this earlier, so we will see how the system uses each one of these modalities and chooses some signals to help recognize. So for the hand shape, we use EMG sensors, which give information about segments of the muscle that are activated. So that is a device that we use, and actually I'm like wearing the device right now underneath my shirt, which just means that it is very inconspicuous and you don't really notice somebody that's wearing the device. And for the orientation, we use the gyroscope. For location, we use accelerometer, and movement is again detected by accelerometer. Well, it's detected by a combination of accelerometer and orientation. So for facial expression, this is a question that I get a lot. It's like, how do you detect the facial expression? But since we're facilitating conversation between people, some of it we can assume that the person that is involved in the conversation will also be able to discern the signs. So that was the device. And for the comparison methods, although we tried a lot of different techniques, we came upon DTW, the dynamic time warping, which measures similarity between 2 temporal sequences which vary on time and speed. So this is used extensively in the speech recognition domain. It is lightweight for the short signal we have, and it can handle time shifts, which happens a lot when someone is repeating a gesture. And it gives us a normalized distance score, which we use to do the ranking. So this is more like a pictorial demonstration of what I talked about. So these 2 signals were generated by the same underlying process, but as you can see, there is a lag, and they don't exactly match. But since DTW finds a good alignment, which is seen by the dotted lines, it still gives you a good result for this. And this is the real signal that we used. So this is the accelerometer on the x-axis. For the top 2 are the all morning. So this is a gesture all morning, which is performed by that motion. And the other one is can't sleep, which is another gesture. But on the accelerometer axis, as you can kind of see, the shape patterns match, but there's a lag between them. But here you can see that we don't really see any shape similarities. And this is also demonstrated by the score that we get, which is 0.04 for this. But for this one, there is almost like 7 times higher distance. So DTW helps us choose between these 2 signs. As far as EMG goes, the sensors we use are commodity sensors, and they don't really have very reliable EMG data. So what we did was we differentiated the signals based on activation energy for different segments. As you can see, the two signals here are generated by the same sign again all morning. And the last one is a different sign, again, can't sleep. So the activation energy difference between these 2 is 3,364, while it is closer when the two of the same signs are compared. So for methodology, it is a very simple technique to collect data. We use smartphone or a computer to do to collect data over a certain amount of time, and then we combine that data. We do some feature selection on it, do like general normalization, and store it in the gesture database in an annotated way. And while the gesture is being performed at recognition time, so we do the same kind of pre-processing and get the gesture from the database and do the comparison techniques that we talked about earlier, and we combine them to get similarity rank. For this paper, the combination algorithm we used was we gave equal weight to accelerometer, EMG, and orientation. So we got the similarity rank by getting all the distances first, normalizing them, and then just doing a weighted combination. We did do some search optimization towards the end to make sure that the recognition time stays under half a second, which we took as a threshold for being real time. The selection of gestures, we selected 20 gestures for our overall experiments, and we selected them in a way so that they are very similar in at least one or two of the modalities, but they are different in another one, so that we just wanted to test if the system is able to still recognize or differentiate between them. So this test was done on 10 users, and so this result that you see is 13 signs, mostly for space reasons. So in this confusion matrix, you can see that when we use just one modality, which is accelerometer, there are a lot of false positives. But if you use all modalities, then they kind of clear away. And you can see that it is correctly identified for these two signs, which are very similar. One sign is orange and the other one is bird. So as far as the time for the recognition is, when we increased the size of the database, the recognition time went to half a second. It crossed half a second right around 60. So we started to do some optimization, search optimization. So now we'll talk about what else exists out there as far as gesture recognition. There's some work that uses the Kinect sensor, which gives you depth information. There's a lot of work with data gloves, and there is some work with cameras, and there are some other works with multiple cameras. But the problems that these approaches have is that one of them is that the camera and the Kinect base are very environment dependent, so you can't really expect it to work outside. So it has to be in a lab setting. And because it involves video processing and image processing, most of them are not real time. And the cost for having these equipments like everywhere that the conversation can take place is high. And also the data gloves are pretty expensive. And the usability goes down because of these reasons, and also because they are kind of invasive. There was some work that used a surface EMG and accelerometers, but the recognition was not real time, and some work that handles one hand at a time. But we were able to use our system to recognize one-handed as well as both-handed gestures. To conclude, we were able to use commodity sensors right off the shelf and design an algorithm that was non-invasive. It's very usable. It can be extended because the user is able to train his or her system by themselves, and we could get the double-handed recognition. So for the work that we are doing now and for future, we are looking into continuous processing of signals. We're looking at including context information while doing recognition because American Sign Language or any other sign language is very dependent on the context that it is being used in. And we want to use grammar and correction and also incorporate facial expressions. Yeah, thank you. Yes.
So basically, you show some results by like only use accelerometer to get some results, like also together to get some results. So because the EMG sensor is very tricky sometimes.
Yes.
Try like if you don't use EMG sensor, what's the results look like?
Yeah, so I had one slide in which I just used accelerometer. The result was about 81% of accuracy, but it all depends on how you, what kind of signs you use. So if the signs do not differ on the hand shape, then you will get better results. But if you choose signs that are very close in everything else but the hand shape, then the results will suffer, because that's the only thing we're using the EMG sensors for, is to classify between signs based on the shape of the hand.
So for Wearable system, you said you use four flow cosmetic.
Yes.
So basically combine all the 10 user data together and divide the 4 parts. Is that what you do?
Yes.
Okay, so you assume it's you're doing the same one. So have you tried actually do like data collection in multiple sessions?
Yes. So we had the same 10 users that we used for the experiments, and data was collected at different times. So they would perform the sign, and then there was like a module where we're actually like recognizing it while they were doing it, if there was enough data, if there was like 3 iterations already, and then they would be invited back again, like after a day or in another session, and then we'd collect the data again. Yeah. Yeah. Thank you.
All right, while we switch speakers, I have a question.
Yes.
You mentioned you considered, I think you said 0.2 of a second to be kind of real time.
For this work, we said under half a second.
Half a second,
Yeah.
sorry. So I'm curious, how fast do people actually sign in real life?
So we collaborated with a sign language instructor, and it really varies on how fluent they are in sign language, much like how we talk. But some applications for this, especially in situations where we're using it for to help like accessibility or disability, like a slower recognition time was accepted, up to 5 seconds. But for like normal conversational place, it is much faster. Yeah.
All right, thank you very much.
Thank you.
All right, so those were our 3 long papers for this session. We're now moving to our first short paper, which will be presented by Terry Misu from Honda Research Institute. And this paper will discuss Look at Me, an augmented reality pedestrian warning system.
Thank you. So this work was conducted by the first author while he was an research intern with us. So the motivation of this work is, what we have implemented using our hardware is this, please look at this. So this is like a augmented reality pedestrian warning system like this. So this is actual driver's view from drivers. So let me clarify the problem. The problem of current visual pedestrian collision warning systems is that it cannot tell where the detected pedestrians are located. For example, for some system use icon like this, but like a warning is given through the a visual symbol, meaning that drivers need to further locate pedestrian for appropriate decision and reaction, such as if it's very close, driver has to do hard braking, and if it's far, it's soft braking is okay, or change the safety margin by steering, or something like that. So our goal is this a warning method to overcome those problems. So this is our overview of our study of using our augmented reality display in the car. And the objective is to develop a new pedestrian collision warning system taking advantage of volumetric heads-up display. Let me explain the hardware later. And the guide, which will guide drivers' attention for fast detection and the localization of pedestrian using augmented reality. And the research question our research question include can spatial information provided by the AR heads-up display improve drivers' performance further, or change braking behavior. That's one thing. And the second thing is the can visual warning on the heads-up display affect some stopping distance. Those are our research questions. And we conducted experimental user study with 16 participants. So our hardware is like this. In the car, we have a heads-up display here, and the combiner comes here, and this hardware can show like a virtual image in the target distance. Meaning, this means it's not like using perspective, but like actual image, virtual image goes to actual target distance. So that's a very specific characteristic of this display. And this is like achieved by fast switching image distance. So, but like for like a driver, it looks like a real volumetric image. And using this display, we implement the pedestrian warning system I showed on the video, and we did user study. Well, this is like a complete Wizard of Oz setting. This means like we predefined pedestrian locations. We define the target distance to time to collision is 2.5 meter, 2.5 second, and 5 seconds. And we used a very accurate GPS, which error rate is usually less than 20 centimeter. And we triggered the warning when the car passed some specific points. And we simulated test. We conducted simulated test using this real 3D heads-up display. So let me summarize our interface design. We compared those two designs with no warning case. One is kind of traditional warning, like this. Just as a usual heads-up warning, when like a pedestrian is detected, the system show like a sign icon, like a please brake, like this. The second design is using like augmented reality. That is the image, the warning appears close to like a target distance, and keep stay in the position. Like let me summarize. In summary, the traditional warning shows a brake sign. Our proposed virtual shadow concept shows a actual shadow of pedestrian, like this. And the traditional warning notifies the driver the presence of the pedestrian in vehicle's path. Like ours notifies direction and the distance of the pedestrians. And while the traditional warning sign remains as the same at the center of the display, regardless of the target distance, ours is attached to the actual pedestrian and appears larger as the car approaches. So these are summary of this difference. And we conducted a user test using 16 test drivers, and we measured those variables. The first analysis target is braking behavior. This graph shows users' vehicle speed, and this is like acceleration. So this is time zero means like the timing the pedestrian appeared, and as you can see, this large drop of this acceleration, meaning that driver started braking, and we defined reaction time by like the duration from the onset of the stimuli to the actual driver's braking behavior. And we also use like a time brake duration, how long driver is braking, and the Gmax means how it's hard brake it is. And the second analysis target is stopping distance, and how far from the cars when the vehicle stopped. This is defined from the gap from the target pedestrian, and we compared driver's performance using above 4 variables. Yeah, let me. This is very. Please, the result. Please, these are our proceedings in detail. But in summary, both methods reduce reaction time, driver's reaction time. So by using a warning system, driver can come to know the presence of pedestrian anyway. And by the conventional traditional warning led to always like a hard braking. So meaning that regardless of the distance to the pedestrian, driver always brake hard. But like by using our design, driver could like coordinate like how hard he should brake. Like for close target, a very hard brake, but like for distant target, oh, it's okay not to brake. I don't brake so hard or something like that. Yeah, this is like in summary, like both traditional and proposed methods reduce the reaction time, but like a virtual shadow result in smoother braking in both near and far targets. Yeah, and the future work includes like maybe the question you may think is this intelligent UI? Or maybe not, but like I think it's very important factor to be intelligent because like it's always balance between amount of information and annoyingness is like a trade-off. So we need to like consider drivers' awareness of like pedestrian and the meaning that we don't should not show the warning when driver is already aware of the target or things like that. Okay, let me. This is summary. Okay, thank you very much.
Any questions?
So, Chang again from Georgia. So, I have a question because how did the user study? The user actually driving a simulator or driving a car?
It's actually user drove the car. Actually, yeah. In our parking lot, actually, the setting is like this. Yeah, driver drove the car, and we put several cars on our parking lot. And after passing this line, like the pedestrian comes.
Yeah. So, my question actually because when you drive, so you're highly focused while driving, or something else.
Mm-hmm.
So this experiment now, because the driver knows there's something will show up,
Mm-hmm.
so you get prepared. But when you in real driving, your focus is different. That cognitive distribution is different.
Correct.
Maybe I don't know whether you have some like in the future how you can move this forward to real application, something like that. Yeah, and another thing is actually whether the information is necessary. Like when you're driving high speed,
Mm-hmm.
whether you have enough attention to pay attention. Okay, what's the distance of that like participant show up and the like whole logic is.
Mm-hmm.
Maybe just showing okay, there's participant you need stuff.
Right.
Okay, there's some trade-off.
Right, right. That's why I think we need like a further study or like a driver monitoring as well. For example, yeah, as you said, like if driver is not looking at front, like a visual stimuli is not good media modality. For example, audio or sound is better or something like that should be investigated further. I agree.
All right. So while we switch, I'll ask a question as well. So I guess related to that of kind of driving really high speed, how people react, or whether they're not paying attention. Have you thought about using a different metric? So currently you're looking at stopping distance and the braking behavior,
Mm-hmm.
but can you define what the right behavior is, and then think of a measure that's kind of a distance from the right behavior,
Mm-hmm.
so that then maybe there you can start to optimize the algorithm to warn the right way.
Yes, yeah, we are actually like analyzing and investigating further like this data. For example, we are now investigating driver's gaze behavior, or this kind of like everything should be integrated. Like, yeah.
All right. Very good. Thank you.
Thank you very much.
Our final talk for this afternoon session is a TIIS paper. It will be presented by Roberto Vezzani from the University of Modena in Italy. And the paper's title is A General Purpose Sensing Floor Architecture for Human-Environment Interaction.
Thank you for your introduction, and thank you for giving my opportunity to present my sensing floor architecture. This is a TIIS paper, so you can download from the link. And the work was initially founded by a ceramic company in Italy, Flooring. The goal was to transform a traditional floor into a sensing floor, and we had some requirements. The first was a low-cost architecture, and we need to fulfill some other requirements like scalability, reliability, and finally, and the most important thing, the sensor should be invisible to the user. Look at the picture. This is a sensing floor, so it is invisible to the final user. And the applications are a lot, ranging from security for surveillance applications, to social behavior analysis, to collect data from public installments, to building automation, to control lights, and finally, as a human-computer interaction device in order to control some interactive applications. And during the project, we have considered all the aspects from the sensor, so from the hardware device, to the communication protocols, to the low and high-level data processing, and finally, we have developed some applications and use cases. All these aspects are included and detailed in the journal paper. First of all, the hardware device, we have a patent on that, and the principle is that the resistance between two metallic wires is changing if the pressure on top of them changes. And then just a few instructions if you want to make your own floor. So just create horizontal and vertical metallic wires. Between them, you can place a conductive polymeric layer. And then you have to use flat cables to reach a capture board. And finally, you can cover with flooring ceramic tiles, of course, on top of them. And the tiles are useful because they distribute the pressure on more than one sensor, and they protect and hide, of course, the sensors for the requirement. The commercial version is much better, of course. We use a printed circuit, and the size of each module is 1 by 2 meters, and each module contains more than 100 sensors. For example, in our lab, we have installed a 6-module floor. So we have a 3 by 4 meters device containing more than 700 sensors. This is our lab prototype. We also developed the low-level processing unit. So first of all, we map each sensor value into a pixel of an image. Then if you have multiple modules, you can merge them into a global image. And of course, we can use image processing and computer vision techniques in order to understand what happened on the floor. So we use a traditional video surveillance pipeline to detect people and to track along time. And finally, we adopt a random tree classifier to recognize the action or behavior of the people on the top of the floor, just to understand if the person is walking, jumping on its own place, or if the person is falling down, and so on. These are some preliminary results on action recognition, so the accuracy of the system is very, very good. And both the data from the low-level processing unit and high-level information are collected on a network server and distributed to a high-level application. Let me show some final prototypes. This is a surveillance and safety application. An alarm is triggered if the floor detects a person for surveillance or if a person falls down for safety. And This is a setup which I have installed in Historical Museum in Lecce, in Italy, and the application is very simple. Walking on the floor, you can discover hiding paint and or pictures from the city. So people are encouraged to scan all the floor in order to show all the complete pictures. And this is another application. It's called Street View, selecting a starting point and end point using a map. We collected all the images from Google Street View, and so walking on the floor, you can have a sort of virtual tour between the 2 points selected on the map. As I told you, the research activity in our lab are mainly focused on image processing, computer vision topics. We are currently working on improving the low-level processing steps from people detection, tracking, and behavior recognition. We are also integrating everything in an embedded system, but we need new collaborations in order to develop a more interesting and more impressive application for interaction. So if this is the case, please contact me after the presentation, and thank you again. Also on behalf of the other authors of the paper, this is the link of my lab, and thank you again.
So our lab is very close to work. Our lab
Thank
also
you.
working on like manufacturer for the same researchers. So there are two questions. So one is the price, and another thing is power. So and another thing is the resolution. So I didn't see that like you go over that slide very quickly. Like what kind of activity can be had? Like what's the resolution of the floor?
Oh.
How many people can be had?
Okay, let me go back to the price is close to 200 euros for each square meter. And the resolution is 10 centimeters for each direction. And the sample rate is close to 20 frames per second. And so each feet is able to select 2 or 3 pixels in our image or 2 sensors. So the resolution is not enough for rehabilitation or in order to understand which is your posture. But it's enough to understand if there is a person, and if the people are not touching together, you can distinguish all the people on the floor. That's all. Thank you very much.
Any other questions? So I have, I guess, a couple things. One is you mentioned the resolution in space. Is there does it measure pressure too, or just binary kind of you're touching here or not?
No, it's a resistance, so is an analog value, but of course it depends on the position of the feet and the tiles over them. So it's not exact your weight.
Mm-hmm.
We cannot understand your weight, but it's not a binary flag.
Got it. And then as far as the technology, is it possible to scale it down if you had narrower strips that are closer together, or is there a fundamental limit with the technology?
Okay, I think that the problem maybe is the communication, because you have to integrate in a hierarchical manner more modules.
Mm-hmm.
But for example, for this room, the image is not so big, so any computer vision can manage such a kind of images in real time.
Very good. All right, and I see a connection to the second paper, perhaps, where you could look at those pictures and try and figure out what movements people are making on the floors, perhaps. All right, so that wraps up our section. I think next up is the banquet, which will be in the stone room, or the cocktail hour, which will be in the stone room at 6 o'clock. Thank you, everybody.